Hello, this is my 8th attempt at doing this question. Not because I can't do this question, is that because every time I try to record myself doing this question, something terrible happens. Or someone needs something of me. But as far as I'm concerned right now, I should be free to do some maths. And hopefully this question is going to be quite entertaining. Let p of x be a polynomial cubic, x cubed plus x squared minus 1. The first part of the question is to show that this polynomial, this cubic, has precisely one real root. The second part of the question is to show that that root is irrational. Now, I'm going to be focused on the first part of the question now, which is my approach to it is going to be to kind of graph it or roughly sketch it. And to do that, I need to know its stationary points. And to do that, I am going to differentiate and solve for x to find the x coordinates of my polynomial. Sorry, not polynomial, stationary points. Now, I know if I denote my stationary points as follows, S1 and S2. S1 is minus 2 over 3, and I think my y coordinate is going to be minus 23 over 3 over 27. And S2 is going to be 0 minus 1. Now, this is roughly what this would look like. Okay. And my axis, and like this. This is going to be S1, and this is going to be my S2. Make it slightly longer. Now, I know that cubics always, or at least must always have at least one real root because they must cross the x-axis. Bear in mind, this polynomial is like functions like these are continuous throughout all x. So if they start from negative infinity and go to positive infinity, they must at least cross the x-axis once. Now, I can say that because both maxima and minima of p of x are below the x-axis, and as x tends to infinity, my p of x will also tend to infinity, and the same is the other way around. And p of x is a continuous function. This implies that p of x has precisely one real root. Continuous, for those who don't know, a very simple way to understand what continuous function is that you can draw it without having to lift your pen. So for instance, an example of a non-continuous function is this, because I have to lift my pen to go to the other side without writing. But this, for instance, if I were to change it slightly like this, would be a continuous function. This was a very poor explanation of what continuous function is, but we don't have to get to the nitty-gritties of it, so it's fine. Now, the second part of the question is quite interesting. Because I need to show that this real root, which I will denote as alpha, is the root, is irrational. Now, to understand how to do this question, I'm going to employ the use of a theorem called the rational root theorem. which states that the possible candidates of my rational roots that I can have are of the form of the coefficient of my leading term and divided by -1, my constant term, and all of its divisors. So for instance, my rational roots candidates here are plus -1. So p of 1 and p of -1. But before I actually go on to explaining how this is going to work, let's look at what the rational root theorem even is. Okay, I have done this like 50 times, so if I am too fast, it is completely my fault. Now consider you have a polynomial f of x, which looks like this. This is an nth degree polynomial with constant term a(n). Now let's say that a rational root, that this polynomial has a rational root. By the way, rational means in this case, for instance, that if my root is r and it's a rational number, it can be written as p and q, p over q as a fraction, where p, q are part of the set of integers, so they're integers, and p and q are co-prime. That means I cannot read. This is the simplest form of my fraction. I cannot simplify it further. Now, if r, actually better to go with p over q, is a root of f of x, we know by factor theorem that's not how you write t. Apologies. F of p over q is equal to 0. Now, if this is the case, then I can just substitute my x's with p and q's, and I'm going to be left with the following. Okay. Now, this is quite important. The next step I'm going to do is I am going to multiply everything by q to the n, so this term here, and I'm going to be left with the following. And let's say I am going to show one extra term for clarity. Now, the next thing I'm going to do is the following. Okay, I'm going to give myself some bit more space. I know it's lagging a bit, I apologize for that. Okay, that's fine. I'm going to rewrite this. I'm going to keep my first term on this side. a1pn is equal to minus q a2pn p to the n minus 1 a3 pn to the minus 2, it should be a 2, q all the way to an qn minus 1. Now this statement is crucial because it implies that q divides pn, p to the n. That means that the coefficient, that the possible roots of the if my polynomial has let's say coefficient 1 of my highest degree term, so if a1 is 1, then any rational root must be an integer, and that's very important. Now, there's a term for these kind of polynomials which have a coefficient of the highest degree term 1. They're known as monic polynomials, and they are incredibly powerful polynomials. And I'll show an example of why they are incredibly powerful. And I did not know this until like 2 days ago, and I found this to be the coolest thing ever. Now, back to the actual problem. I think I'm kind of going on a tangent right now. I know that my possible candidates of rational roots are plus minus 1. So P1, which is equal to 1, and P minus 1, which is equal to minus 1. Is that correct? Yes. Now, none of these satisfy our condition that has to be equal to 0. Therefore, 1 and minus 1 are not roots of px, and because these are the only possible candidates, the real root, the actual root alpha, must be irrational. Now, if I were to actually write this out as a paragraph, like a kind of statement, any rational root of p of x, not only it must be an integer, must be an integer because p of x is a monic polynomial. The only possible rational roots of rational roots by the rational root theorem are plus minus 1. However, neither of these are actually roots. Therefore, alpha is irrational. And I think this is very, very cool. And that's the second part of the question done. I think it's very cool. I don't think this is the actual proof of the rational root theorem. I think there's a nicer one somewhere else, and this is more to show what it means for a monic polynomial. Why a monic polynomial, if it has a rational root, it must be an integer. I'm going to do. I don't know if I should do a separate exploration of that in a different video. Actually, you know what? Let's do it now. Consider the following. Hopefully, if my OneNote, that's completely different part of my OneNote. Okay, now consider, let's say, root 2. Okay, I need to prove root 2 is irrational. Now, there's a standard way of saying that root 2, assume root 2 can be written in the form of p over q, where p and q are integers, and then you show by contradiction that root 2 cannot be rational. However, there's a different way, is where you construct a monic polynomial by saying, let's say x is equal to root 2, therefore x squared is equal to 2, and your monic polynomial is going to be x squared minus 2 is equal to 0. The only possible by rational root theorems candidates of this polynomial rational roots are plus minus 1 and plus minus 2. Now, if I call this f of x, I can check that f of 1 is not equal to 0, it's minus 1. F of minus 1 is also not equal to 0. F of 2 is 2. F of minus 2 is equal to also 2. Therefore, none of these are roots. Hence, we can conclude that root 2 is irrational. Now, this is a very simple example, but if I were to extend this to something like root 2 plus root, let's say 3, which is, I think, slightly more complicated to prove by the standard contradiction method that you're taught at A level. So let's construct a polynomial first. So we say that this is our root. That's not an x. Apologies for that. And I want to construct this polynomial very nicely. This is equal to 5 plus 2 root 6. Is that correct? It should be correct. It's not, it's embarrassing. And now I am going to get rid of the radicals. Get rid of radicals. What a funny statement. Apologies for that. I am going to do this. This is going to be 4 times 6, which is 24. And this is x to the 4 plus 25 minus 2x squared minus 10x squared into 24. And I'm left with the following monic polynomial. Now we know, for instance, this is a hidden quadratic, but it doesn't really matter. The possible candidates here are plus minus 1, because both I think I didn't state this before, but let's say if you have like x squared plus 2x plus, let's say, 10, the possible candidates of rational root are plus minus 10, plus minus 1, plus minus 2, plus minus 5, and so on, all the divisors of it. Technically, if we extend this to non-monic polynomials, if you have like P and Q, I'm using way too many P and Qs. My rational roots are all the divisors, all the divisors of P and Q. So in this case, we have 1 over 1, so plus minus 1. Now, if I call this P of x, P of 1 is equal to not 0, and P of minus 1 is also not equal to 0. Therefore, we can conclude that root 2 plus root 3 is irrational. Again, I have like skipped a bunch of steps where I state how I know everything. But yeah, that's one way to do this, and I think it's very cool and it's very much worth an exploration. This, I think, a number theory topic, and I very much enjoyed doing this. I'm quite sure you can like make things much more complicated, and like the power of monic polynomials is not to be underrated, and it's definitely something I advise anyone to like go out and look. The whole point of me even doing this is to learn it and then understand it by explaining it on a stupid YouTube video. Which I must say, when it comes to the YouTube videos, I've received a lot of support, and which makes me quite happy to see that there are other mathematicians, aspiring mathematicians, or even non-mathematicians who like to watch my videos and think it's cool that doing maths is cool. I don't really know what to say, but yeah, I very much appreciate it. If you have made it so far into the video, I congratulate you. And yeah, I guess I'll have to end the video now because I've run out of things to say, and my social battery has been deteriorating by the amount of times I've been trying to do this stupid video. The video wasn't, I mean, no, sorry, bye.